Hey everybody, Cash Choate with Choate Engineering Performance. We are 2023 SEMA show, place to be, at our booth with our friends from MAHLE. And I've got Eric here, and he's on the motorsport side.
Yes, sir.
And we're going to be discussing today a little bit about a really cool build that we've got coming up. So stay tuned. We're looking forward to talking about this and breaking it down for you guys. All right, so we are going to be discussing a high horsepower LML Duramax build for Cody Pulliam. Everybody knows Cody. If you've been to any dyno events, it seems like in the diesel world, Cody's there. He's always running the event for UCC and a bunch of others. Also a winner of Diesel Power Challenge. Very, very, very well known in the community. So we're going to be working with him to build a very high level horsepower Duramax build, chasing some numbers, and so we're bringing in the best of the best. So I'm sitting here with Eric at MAHLE Motorsports, and he's going to be discussing a little bit about some of the challenges that we know that we're going to be facing with this build, and Pistons is definitely one of them.
Absolutely. Well, and as we've been talking, diesel is kind of an interesting performance aspect because in the gasoline world, cast piston is stock, it's junk. If you want to build power, you go to a forged piston. We know that's not always the case with diesels. There's a lot that you can do with a cast piston, a modified cast piston, things and features that you can add to it, and you can have a very stout, robust piece before you have to advance to the full forged. And in the diesel world, there's actually some disadvantages to forged pistons. However, for the power levels that you guys are talking about, we're going to be looking pretty closely at a forged piston. The biggest advantage is we can build that to whatever configuration you need for that application. If we need an anvil, we can build an anvil. If we have to fine tune it, finesse it, we have that ability to do.
Yeah, and for the guys tuning in, we're talking right now, this range is going to be north of 2,500 horsepower build. So you guys kind of get an understanding of what we're talking about. As for your truck, what your application, what your needs are, may very well, most likely be different than what we're building.
Oh yeah, and there's a place for both, and but you're stepping into a realm where you can add all the bells and whistles to the cast parts, do everything you can to fortify it, but getting into the realm where we need to build a dedicated forged part for what you're trying to do.
So a lot of the guys that are listening are not machinists. They don't know a lot of times the difference between, it's so funny when you hear somebody say billet, the word billet, and they don't understand what the actual meaning of billet is.
Sure.
They think billet is some type of material, some type of alloy or super alloy or something, but actually it's just nothing more than a solid piece of material that you machined out. Now the differences between cast and forging, Eric, if you'll kind of expound on that for us so that guys can understand. I'm trying to start from the very base elementary part of the piston and work our way out.
Yeah. The casting in its simplest form, you're pouring liquid metal into a mold to form this base shape. There's a lot of advantage to that. You can actually make some very lightweight, intricate castings. There's things you can do with that pourable liquid metal that you can't do with a forging, but there are some strength deficiencies in that, just the way that the casting process works, compared to a forging where you may start with that true billet, a slug of material, and then it's heated and under pressure it's formed, and so you're actually pushing the shape into place with tremendous amount of heat and pressure to form that, and it transforms the grain, the structure of the material.
Now it aligns the grain. Is that correct? It aligns the grain when it's a forging like that.
Yep, there's multiple ways to do that, and the irony is you can cast and forge the exact same material. The alloy composition will be exactly the same, but at the end of the day, after all that processing, the forged material will actually be stronger, even though you're starting with two duplicate materials.
Right.
So there are some inherent advantages just in the forging itself, beyond what we can do on the design side and machining manufacturing.
Right. So going to the cast piston, horsepower rating on this, I know guys that are actually running these things, I hate to throw a number out there because there are so many different variables. So for that reason, I'm actually not going to even throw a number out there, but I will say...
I'll step out on that.
Are you?
Ledge.
Okay, go ahead.
So what we recommend is you get into 1,000 horsepower 1,200 horsepower, that's probably the range that you're going to see the limitation of the cast. Now, everybody will have a story about how they pushed them to 2,000 plus. Okay, great. Yeah, it is possible, but do we recommend it? No. But if you want a ballpark number for our Duramax cast, that 1,000 to 1,200 will work there.
Yeah. Well, there's something different too about this. Now I'm looking at this. This is, so we're talking about an LML platform, guys. Now, one thing that I noticed different is this ledge for this ring is different. It's not actually like the factory.
No, on the performance cast pistons that we sell through Motorsport, we do not sell a factory style bowl. We modify that geometry. There's some things that we've done differently with the shapes of the casting internally. Obviously, we add our script coatings to everything we do, but yeah, we do modify that for a performance application.
Yeah, the thing that we've seen before on the piston cracking is generally, your crack starts, it's actually a hole that seems like it burns into the piston first, and it's always over the exhaust valve from that transfer area, because that's the hottest portion that we have of that piston. All the heat gets trapped right there, and with the re-entrance style piston, as it's trying to reverse rotation, it just builds a tremendous amount of heat, burns a hole, and everybody thinks it's a crack, but it actually starts at the hole first.
It starts with a crack.
Yeah.
It starts with a crack. With the edge of the bowl, it's the hottest point on the piston. It's also the highest stress. So if you imagine the force pushing down on this and the pin pushing up, you're trying to fold that piston over the pin. So that little small edge right in that corner, not only on the exhaust side, but directly in line with the pin, highest temperature, highest stress point. So typically what happens is you'll almost always see some sort of crack that initiates there, but then as that crack expands, it starts to burn, and in most cases, it burns and it covers up the initial crack. So what you see is the hole, but almost all of those that burn through start with a crack, and almost always on the edge of that hole.
I think a lot of times there's so it's interesting to note that we'll see almost always on these pistons, we'll see a crack that is running parallel to the wrist pin.
Yep.
On a 7.3, I don't know if you've noticed this, I've seen this a bunch of not. It's always 90 degrees of rotation, but you look at your exhaust valve, and where the location is of that exhaust valve and the transfer of the heat over, it starts to right there.
And an offset bowl in the 7.3.
Exactly.
So we're changing the entire geometry, the way that the stress is distributed through the part. So combination of factors.
Very good point. Yeah. So what is the temperature rating of this, and what is the type of coating that's on this piston?
Now that I will not make up.
EGT is just a number, man.
I'll throw out a horsepower number, but EGTs, there's so many variables that come into that it's very difficult to say this is safe, this is not.
Right.
And again, just empirically getting data back, we'll see where 700 works, and we'll see where 1,200 works, and then everything in the middle will fail, and it flips back and forth so much that it's hard to put a number on it. And the variables of how you measure EGT, how far from that chamber are you when you get it, becomes very, very difficult to do.
Yeah, absolutely. It takes a lot of instrumentation that the average guy with a truck going on the road, they don't really know what's going on.
No, EGTs are great for monitoring what's happening, but it's not good for setting this is an absolute parameter or limit.
Yeah, absolutely. So as we're looking at the piston, let's talk a little bit about the geometry of the difference between the cast and the forging. I mean, I've seen the piston boss area is a little different there. We can see that there's a little meat that's added there. We can also see the boss is thicker in certain areas of the piston. If we flip it over, we see the valve reliefs, obviously, that we have. You can see the machining marks here. That's obviously, for the valve reliefs. The witch's hat, it looks to be pretty much the same as far as the bowl is concerned, but what do we got going on?
Yeah, very, very similar geometry in the bowl. We will make some adjustments, accommodation for the compression that we're trying to hit. So if we're punching pockets in it, we may have to compensate the shape of that bowl so that we're not just lowering. Some people don't realize how much or how little volume it takes on a diesel piston to dramatically change compression. So you could punch these same pockets in this part and lower it a full point of compression. If that's your goal, great, but a lot of guys aren't after that. So we'll try to make some compensations in what we do with bowl geometry, if we're putting pockets in it or not putting pockets in it, just to accommodate that. Pin bosses, we pretty much are trying to fortify these for some RPM. The stock diesels aren't meant to turn 4,000+ RPM, right? So we're making sure that you want to turn them 6,500 if you can, then it's going to go. Or if you have circumstances outside of your control where the RPM gets elevated, piston's not going to be the first thing that breaks. There may be other issues.
So I noticed right off the bat that the ring pack's actually different on these two pistons. Is it? believe if I'm looking at that correctly.
Yes,
Yeah.
we switched top ring. Actually, on our forged Duramax, we use a factory second ring, a factory oil ring, because those are very good pieces for what they are. The big difference, and this is where it comes into where cast has a huge advantage, is that ring insert on the top for the top groove protection. You cannot do that in a forged piston successfully and have it last like it would on a cast part.
So this is a mechanical lock for the top ring, for the steel insert?
It's alloy. It's part of the casting process that occurs. Just as we're looking here closely,
okay.
This part is anodized, so it looks like it has something in there, but that's just the surface treatment that we do.
So as far as guys, you mentioned real briefly that there was disadvantages, and I think that's where we're starting to go with the disadvantage for application is everything, right?
Yes.
And that's what guys are always looking for. The silver bullet. What's the best? You've got stage 1, stage 2, and stage 3, and stage 3's got to be best because 3's more than 1.
Right.
And that's really it's a terrible way to design an engine component or part, because it's all based off application. So your hard anodized top ring, its longevity versus the steel insert.
Yeah, it doesn't compare, and that's the real disadvantage to the forged part, is eventually you're going to pound out that top ring groove and you're going to have blow-by issues, seal issues that come up. So we try to fortify it the best we can with adding the anodizing to help it protect against wear. But ultimately, if you're looking for 1,000 plus miles, the 50, 60, 80, 100 plus 1,000 mile durability, that cast part is really where it's at.
What would you, if you had to put a number on? And I know that's impossible, and I even hate to say that because there's guys call us all the time and they want to know, okay, well, give me a horsepower number. The thing about it is when you make horsepower, you're making heat, you're making pressure, and you're making it at different RPMs, different levels, different duty cycles. There's so many variables to that.
Well, and the interesting story that I like to tell with that is we've had same builder building multiple engines with the forged parts. So his combination is the same, and he's got one truck that gets 3,000 miles and it's got blow-by going through it. He's got another truck that's 40,000 miles still running down the road, and it's just fine. And he's like, well, what's wrong with that? The pistons in this engine that only got a couple thousand. Like, it's not a piston issue. You may have built the same combinations, but once it was out of your hands, did it get tuned the same?
Exactly.
Is that driver and that driver, how are they loading it the same? So those variables is what makes it difficult to say that's good for 10,000 miles, or that's good for 3,000, or it'll go 50.
Right.
It's those variables, and exactly as you were saying, the combination and usage that come into play.
Yeah, that's really a difficult thing to nail down. I know everybody wants to know, they want to know numbers, but it's an algebraic equation. Right.
Well, what we ask comes back to that application. How are you going to use the truck? Is this your daily driver that you want to go race or pull a sled occasionally? You could probably get away with the cast part, because again, we can make the cast part strong enough in most cases. If this is your dedicated race truck, or if it's not your dedicated race truck, you should probably steer away from the forged part unless you're willing to take that risk and understand that it may, depending on how you use it, need some freshening.
So we both are seeing DFL coatings, I'm assuming, on the side for the skirts, the dry film lubricant, or?
Yeah, same coating. This what we call Grafol is the same coating that we use on almost everything that we make, whether it's a gasoline, a diesel, heavy duty diesel, or full-on race parts. That same coating works in all those applications.
So is this a ceramic or polythene, or what's the?
Yeah, this is a true heat barrier coating. There's different approaches to that. We take sort of the insulated version of it. The biggest drawback to some of the top coatings is you have to make sure that there's not delamination and fracture that occurs. So we've kind of settled on a composition that we feel is more forgiving to deformation. That piston, it feels very solid, but when it's operating, it's moving around a lot. And with the temperatures and everything that it sees, we want to make sure that the coating that we have stays put, because that can actually lead to detrimental effects if it doesn't. So
we're looking at a couple of things here, and I'm seeing the reliefs between the gas reliefs between the intermediate rings. Can you talk about that for just a little bit, and what the purpose of ring sealing and kind of how that relates to the geometry, the purposes of it, and things like that?
Yeah, that's what we call an accumulator groove, and it's just volume. There's always going to be some leakage past the top ring, no matter what we do. If we could make it perfect, we would, but we haven't figured out how to do that yet. So that gas that gets past the top ring, ideally, once it's past the top ring, we want to get it out of the crevice volumes between the rings as quickly as possible. Larger second gaps help with that, and there's various methods that you can do to use that. The detriment being, if you start to build pressure between those rings, then it's starting to lift up on your top ring, and that's not how the top ring seals. It needs to be flat against the bottom of the groove. So just adding a little extra volume in there gives those gases more room to expand, so it doesn't build that pressure quite as dramatically. It's very small, but it can have a noticeable effect. And the other, the real flip side of it is we've never seen where that volume really hurts, so we'll put it on as many applications as we can so that there is that added layer of protection sort of built into the part without having to change any other variable.
So is this going to run a Keystone top?
The cast will run Keystone. We go ahead and convert it over to a rectangular flat ring on the top.
Okay.
The Keystone will actually aggravate wear, which is what we're trying to combat here.
Right.
And the flat rectangular ring will actually seal better against the piston surface, and you can, if you can retain the shape and don't deform that flat rectangular ring, it will seal better. There's
a really good video that we'll cut to later that you kind of that you show the geometry basically, and that kind of helps people to understand when we're talking about Keystone rings and flat rectangular rings and the different geometries, how that actually seals and what the ringland is actually seeing. The rocking, the Keystone, like you said, aggravation. Go ahead.
I say that the Keystone is great in a diesel for carbon cleaning. That it's made to move within the groove. That's what helps keep you from building carbon and getting rings that become stuck, etc. But if you're inducing movements when we're trying to protect on an unprotected groove, it's very detrimental to the overall system.
Yeah, that makes perfect sense. We really saw a lot of that problem with the 04.5 to 07 3 1/4 Cummins with ring compaction and ring wear. Really bad issues with those but for a whole other set of reasons. You can definitely tell, like this, you're seeing the tooling marks on this piston where, obviously this is a forged piston and this is a cast piston. Just for those that aren't familiar with machining processes and how this works, you see the textured finish because this is cast, but y'all are actually having to come in with a ball mill, right, and finish that up.
Yeah, and that's, we could leave that fairly closer to an edge forged surface, but it depends on what we're trying to do for weight. There's, again, sometimes you want an anvil, but there's other places where let's put the mass where we want it, take it out of places that it doesn't need to be, and sort of balance that whole thing, reciprocating weight.
Well, we've got it upside down. We can really take a look and see what's going on. And we were talking about this a little bit earlier, and you were explaining the purposes for it. Sometimes it's old technology, but still gets transferred in based off OE. But we can talk about the purpose. I know a lot of guys that have seen this in the diesel world are not as familiar with this because it's more of a gasser thing from days gone by than it is what we see the Ford or the Power Stroke that comes in the Duramax. Yeah. So if you can talk a little bit about, and I'm going to flip this over, and if the camera wants to come in and zoom in, you can kind of take a look, and we'll see these steel inserts.
Yeah, in that particular casting, that's a way of controlling thermal expansion of the skirt. A lot of people confuse them as they're adding strength to the part, and that's not the case. It is there strictly for expansion. It has it's bonded to the aluminum in that casting process, and just the steel expands at a different rate than what the aluminum does, so it controls how much that aluminum skirt deforms under temperature.
So a little bit about geometry, I guess, of pistons that guys don't really understand. When you look at a piston, your natural, if you weren't an engine builder or you weren't a machinist or you weren't into the motorsport side of things or whatever, you'd think, okay, that's a round piston, right? Yeah. It's just a slug. But that's so far from the truth in every shape, case, and form, whether the skirt of the piston, the barrel shape of the piston. Talk a little bit about the geometry that's necessary for that, because I had a funny story. I was telling my friend Dan that works at MAHLE, we had a customer call us and said, I've got a problem with high amounts of blow-by. It ended up being that they trashed the first engine and it shot all the shrapnel in from the turbo, and it damaged the ringlands from the first engine. They never cleared all that out of the intercooler. But when they tried to take and measure the piston, he said, I've got 28 thousandths piston to wall clearance. And I said, well, without removing the piston, how did you know that? And he goes, well, we measured it from the top. So, no.
Yeah, no, it's the reality is if this were a true cylinder, it would probably fail on startup. So there's really two key elements to how we shape the part. One, if you look down the vertical surface of the piston, this has some sort of barrel, some sort of taper, because your top's always going to be hotter than it is at the bottom. So you have to control that expansion. Plus you have to account for the geometry. You know, pistons have a ton of mass at the crown, and then because they're open, that mass dissipates. So it's going to grow and expand differently based on just mass of the piston and where the material is. So we make a shape to accommodate that. Plus you need a shape that runs well against the cylinder wall in terms of wear, friction, etc. So the skirt shape itself is very important. And then also because of that same different rate of expansion because of mass, you have to make the piston into an oval shape. You know, up near the top you can probably be closer to a cylinder, but there's still cases where ovals make sense. You have to be concerned about where head bolts are in the cylinders, because the cylinder isn't round either. So you're accommodating for all those variables. You put ovality in the skirt because, you know, you may not want contact all the way across the face of your skirt. You know, a nice even patch in the center is enough to guide it. Anything beyond what you need for guidance just becomes friction.
Just keeping it from rocking.
So there's an infinite number of shapes that you can do when you combine those variables in terms of combining that barrel, the ovality, and you know, all of that gets fine-tuned to every application that we make. Before we go, I'll show you an interesting part that we've got over on display that kind of shows you some of the intricacy of machining that actually occurs that gives us that flexibility to fine-tune those shapes to whatever may be required based on engine. Turning.
Y'all turn?
That's a turning operation.
How the heck did you turn that?
Really good equipment.
That's amazing.
So you're never going to write your name in the skirt, but the ability to make that any shape that the engine requires, the ability is there. You know, and you have to know what to design it and do, but